Hello, college algebra student. This video is for chapter 6.2, graph of exponential function. So in 6.1, we learn how to use exponential function in a general form of y equal to abx. So in 6.1, a exponential function is a b to the x. So that's a very good form. It's very useful for modeling real life application, but in an abstract way, there's too difficult because you have two unknown or two constant. So we want to simplify a very simple exponential function and classify it as a parent function. You know how we have those toolkit functions that are very simple. So we want to build up toolkit function tools to have one more exponential function. So to do that, we would need to build tables to graph them. And the toolkit function that we'll graph is actually just here, y equal to b to the x. And we use tables to build them. And to build tables, we have to evaluate some x that is negative or 0. So let's review what is meant by an exponent being a negative. So if I have a base, any base b, positive number, and I have it b to the n, that means, and if n is a whole number, that means I multiply n, I multiply b n times. So basically exponent is repeated multiplication. But I can actually do b to the negative n. So what does negative times mean? So it means dividing. And dividing means 1 over b to the n. So that you are keep on dividing by b and it becomes dividing n time. Okay. So b to the 0, that means you don't multiply, you don't divide, you just end up 1. Okay. And what about if I have a fraction? So when we understand b to the negative n, you can think of dividing as the reciprocal of 1 over reciprocal of b to the n time. So if I have a 1 over b, which is a number that is 1 over, like a fraction or something, and I do negative of it, then it would be the reciprocal of 1 over b, and it go back to b to the n. Okay, again, if I have b to the negative, that means the reciprocal to the n time. If I have a 1 over a negative, that means the reciprocal of 1 over b, so it's b to the n. So what about if I have b to the 1 over n? N is a whole number again. So that means I am doing b one fraction of a time. Fraction of a time, you can't even write a b, right? So what does it mean? Oh, it actually just means root, n root of b. And to bring it to the more complicated sense, if I do a negative and also 1 over n, that means I do the reciprocal of b to the n root. Okay, so root 1 over in an exponent is if it's a 1 over fraction, a unit fraction, then it's a root. If it's a negative, then it is a reciprocal. Okay, it's a negative, that means it's a reciprocal. You would never have any negative number results from it, right? So this is a positive number, this is a positive number, these are all positive number. So let's do some evaluation. So because we would need to do that to evaluate tables or build our table. If I want to do 4 to the negative 2, that means 1 over 4 squared, that is 1 over 16. If I do 10 to the negative 3, that means 1 over 10, 3, that means 1 over 1000, right? If I have 1 over already and I do negative, that is just 3 squared equal to 9. 5 to 0 is just 1. Anytime you have an exponent 0 is 1. 25 1/2 time root, that means root 25 square root of 25, that's 5. Whenever I see negative, I do 1 over. And then when I do 125 1/3, that means cube root of 125, and that is 1 over 5. Okay. So let's, if you know how to evaluate this, then you can build a table. So let's try to build a parent function of exponential function where a would be 1. So our really basic exponential function is y equal to bx. B is any number greater than 1. It could be actually rational number, real number, any number. But it has to be a positive number. And then b, if it is a positive number but less than 1, like a fraction, then it's a decay. So you have anyway y equal to b to the x, but two different two different flavor. So to build it, we have to graph tables because b to the x is not in our toolkit function. So we do y, and we choose 5 points, 2, 3, 4, 5. So 0 in the middle, -1, -2, 1, 2, because an exponent can be positive or negative. So theoretically, we could have negative, positive. So let's graph y equal to 2. I think let's graph 3 to the x or 2 to the x. I think in the worksheet you are to graph 2 to the x, so maybe I'll graph 3 to the x. Okay. So 3 to the x would be 3 to the 0 is 1. 3 to the 1 is 3 because just 3 one time. 3 to the square is 9. Right? 3 to the -1 is, remember, is the reciprocal of 3, so it's 1/3. And this would be 1/9. Right? So we're ready to graph 0, 1. So this is what you will be looking for. X is equal to 0, x is equal to 1, x is equal to 2, x is equal to -1, x is equal to -2. 0 go up to 1. 0, 1. 1 go to 3. 2 go to 9. Okay. And then a -1 doesn't go below negative. It's just 1/3. So it's really low, close to the x axis. So it shoot up after it passed through the y-intercept, right? And this side it's not shooting up very fast. And then you can see that there is a horizontal asymptote of y equal to 0 on one side only, unlike rational function that has asymptotes on both sides. This one doesn't. So let's graph another one that is, let's say, a fraction, 1/4 to the x. So we build a table just like before, x, y. 1, 2, 3, 4, 5. 1, 2. Okay, so -2, -2, -1, 1, 2. 1/4 to the 0 is still 1. 1/4 to the 1 is 1/4. 1/4 to the 6 is 1/16. But it would never be negative, right? 1/4 to the -1 is switching it back, so it's just 4. 1/4 is to the -2 is 4 to the 2, so it's 16. So if you graph it just like before, you still have 0, 1, 2, -1, -2. At 0, it's still 1. So just like here, 0, 1. No matter what your base is, when you plug in 0, it's still 1. And then when you have 1, that would be the base, right? 1/4. Oh, okay, it's close to 0. 1/16 is very close. So because this is a decay functions, like going down slowly, it would be approaching the horizontal asymptote on the right-hand side, y equal to 0. And then what about -1? It should to 4, and at -2 it should to 18. So it would go down from infinity and then go down through 0, 1, and then approach the horizontal asymptote. So these are the two versions of exponential function b to the x. B can be any number. If it is a fraction, less than 1, it would slope down this way. If it is a growth function, it would go through 0, 1, and then shoot up. So let's discuss some characteristics of this exponential parent functions. We call them parent function because they are very simple and very easy to remember how to graph. So first is their domain is all real number. You can plug in negative, positive. The range is, so this is very important. In the next, in chapter 3, we'll talk about the range of chapter 4, 6.4, which talks about the range is from 0 to infinity. So you can only see it in the upper half of the coordinate plane. Both of them, even if you are growth or decay, they all have the horizontal asymptote y equal to 0. They both have the y-intercept 0, 1. And like a line that has multiple different y-intercept, this always have 0, 1. And both have the point 1, b. So if you want to know what the base of your parent function is, you look at 1, point 1, you would know. And the two version would be if it is a growth function, you grow from left to right. If it's a decay function, it falls from left to right. or both of them through 0, 1. So how do I graph from the parent function? How do I graph other function? Like an example would be, okay, I'm going to write a very complex exponential function like 5 times 3 to the power x plus 5 minus 2. So this is an exponential function. Why? There is a base and there is a variable in the exponent. That's sufficient. You can have other numbers inside, plus, minus, but it's still a parent function. It's still an exponential function. How to graph this? Do we build table? No. These can be graphed by transformation. So we use the technique that we learned in 3.2 maybe, on a transformation of parent functions now, but we have a new parent function, which is b to the x. So we have the same thing. If you have f of x plus h, meaning you have the things that change. Instead of 3 to the x, instead of b to the x, you have plus and minus in the exponent. Then it is shift left or right. Okay, plus means shift to the left, minus means shift to the right. And if it is a plus and minus outside like this one, then it is up and down. Okay, so this is shift. And of course, we also have vertical stretch and reflection and all those. We'll talk about those later. But these are the major ones. So let's say I'm going to graph y equal to 3 to the x plus 2. So it would be a transform from what? What is the parent function that is transforming from? Transform from 3 to the x itself, right? From y equal to 3 to x by this is outside, not in the exponent, so it is up and down, up 2. So what you do is I'm going to graph the original 3 to the x. I write the 2 point that is important, 0, 1 and 1, 3, right? And then I will graph 3 to the x plus 2. So 3 to the x plus 2 will be here. So how do I do? Up 2. So it would be everything would up to, all the point would up to 0, 1 becomes 0 up to 0, 3. Okay, so this is 2, 0, 3. So this is the vertical asymptote was y equal to 0, right? Now the vertical, no, not vertical, it's the horizontal asymptote is y equal to 0. So now this horizontal asymptote is y equal to 2. Everything push up to including the horizontal. So this would be 0, 3. And then it used to be 1, 3. Now you up to become 1, 5, right? 1, 5. And you know that the rough curve like that. What about shifting if I add something in the exponent? So the second example would be I do y equal to 1/2 x. So did you, and then minus 1. So you see that the transformation is what? From the parent function y equal to 1/2 x, right? And then I have the inside minus 1. So it is right 1. So I'm going to graph 1/2. 1/2 is, down, right? Because it's a down function. I have 0, 1. I have also 1, 1/2. Because 1, b is the point. And then right 1 means what? Everyone shift here. So 0, 1 become 1, 1. 1/2 become 2, 2/2. So you would just do like this, and as if there is a, but then everything stays the same. You still have y equal to 0 as the asymptote. The domain doesn't change. The domain doesn't change. The range is still from 0 to infinity, right? So there's no change. And for the previous one, we changed the so the last one. Oh, I forgot to talk about the range. We changed the horizontal asymptote to y equal to 2. So the range would be from 2 to infinity, right? Because there's nothing beyond less than 2. Nothing beyond the horizontal asymptote. So that's how we do shift, horizontal and vertical shift. When you do a horizontal shift, nothing change much. Only the points change. But when you do up and down, your horizontal asymptote change.